Welcome to Slack Cat Math. Today's lesson is on the inverse of a square matrix. So before we get started with examples, we need to understand what an inverse of a square matrix is. So first of all, we have the term square matrix. So we know that it has to be in a square format. So it has to be 2 by 2, 3 by 3, 4 by 4, or up to n by n. We also know that an inverse multiplied by its matrix is going to give you what we call the identity matrix. So you can see here that the definition of the inverse matrix states that if you have an n by n matrix A and you have an n by n identity matrix, then there is an inverse matrix A to the -1 power, so this A inverse right here, such that when you multiply A by that inverse, it's going to give you the identity matrix. Now, the identity matrix, we'll do I sub 4. So I sub 4 means that it's going to be a 4 by 4 matrix, and it's going to be in the format where you have ones on the main diagonal and zeros everywhere else. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So this is an identity matrix for a 4 by 4. Okay. You can have an identity matrix of any order as long as it is square. We only have square identity matrices. So if this is true, where you take a matrix and multiply it by its inverse and you get this identity, then you know that those two matrices are inverses. If you're trying to find an inverse matrix, you can say, okay, well, if I want to find this inverse matrix, I'm going to try and figure out what do I have to multiply A by so that I can get the identity. Now, matrix multiplication we know is not commutative traditionally. However, we can see here that it is commutative. So when we multiply a matrix times its inverse, or its inverse times the matrix, we can see that we're going to get the identity matrix. So we know that matrix multiplication, when it comes to a matrix and its inverse, is in fact going to be commutative. All right, a few things about an inverse. So we can say that if A has an inverse, then it is what we call invertible. Another way to say this is to say that it's non-singular. And in order to be invertible or non-singular, then it has to meet two criteria. These two criteria is, one, it must be square. As we talked about, this is a definition of the inverse of a square matrix. And then next, the determinant must not equal 0. Now, we haven't talked a lot about the determinant yet, but this will come up officially in the next lesson. Today we'll talk about it just in the form of 2 by 2, but that is a criteria that I want to mention now, and then we'll learn how to find that determinant later on. And because a matrix that has an inverse is called non-singular, then we can say that a singular matrix does not have an inverse. All right, so that's a little bit about what inverses are. And now let's see how we can use them to help us solve different equations or different problems. So number 1 here says use a system of equations to find the inverse of matrix A. So we're going to use the definition that was given such that A times its inverse is going to give us the identity matrix. So starting off with matrix A times its inverse is going to give us the identity. And the identity will be in the same order that matrix A is given. So we can see here that matrix A is a 2 by 2, so we know that it's square. And again, we don't know how to find the determinant yet, but I will tell you that the determinant of this is 0, so an inverse does exist. So now utilizing this matrix equation, we're going to plug everything in and then see what we can use that we already know to find this inverse matrix. So matrix A is 1, -2, -1, 3. We're going to multiply that by an inverse. And we don't know what that inverse is yet, but we're just going to assign some variables. So a 2 by 2 matrix will have a 2 by 2 inverse. So I'm just going to put some variables in here. I'm going to call them A, B, C, and D. So that's my inverse matrix. And that's going to equal the identity, and our identity is a 2 by 2. So it's going to be 1, 0, 0, 1. So remember, an identity matrix is ones on the main diagonal and zeros everywhere else. All right, so now I know a bit about matrix multiplication, so I can just complete my matrix multiplication and then see where I'm left. So I can do row times column here. So doing this row times column, that means I'm going to do 1 times the A. So that's going to give me A, and then plus -2 times C. So actually, let me change that to minus 2C. That was row 1 times column 1. So row 1, column 1 is going to equal row 1, column 1's entry. So that's going to equal 1, doing my matrix multiplication. Then I can do the same thing with row 1 and column 2. So I'm going to go around to each of the columns. So row 1 now times column 2. So I have 1 times B, so that's going to give me B plus -2 times D. So again, let me change that to minus. So minus 2D, and that's row 1, column 2. So then I'm going to look here on the right at row 1, column 2, and that's what that's going to equal. So equals 0. So go ahead and take a moment and do the same thing with row 2. So we're going to take row 2, and we're going to multiply row 2 by first column. So row 2 times column 1, so that times that is going to equal row 2, column 1. So take a moment and do that multiplication and set up your equation. And you can see that I'm writing this equation underneath the one that also has the A's and C's that I did in red. So finishing now, row 2 times column 2. So row 2 here, this row times column 2 is going to equal row 2, column 2 there. So let's go ahead and do that multiplication. And now we have 4 equations. Now what we notice is that each of the 2 equations, or each equation, has only 2 variables in it. So on the left, the 2 equations have both A and C. So they both have an A, they both have a C. On the right, we have B's and D's. So essentially what I've done now is I've set up so that I have a 2 variable 2 equation system, and then I have a second 2 variable 2 equation system. So now I can use what I know for solving systems of equations, whichever way I want. This looks pretty simple. If I just add these 2 equations together, I can cancel the A's, and then I'm going to be left with C is equal to 1. And then I can plug C in. A minus 2 times 1 equals 1. And so then A is going to equal 3. So there I have C, there I have A. My second system, add those 2 equations together, my B's will cancel. And then I'm left with D is equal to 1. And then I can plug D in to my first equation, B minus 2 times 1 is equal to 0. So B is equal to 2. So now I've found all 4 of my variables. And if I go back to what is it that I'm actually finding? I'm trying to find the inverse. So I defined here my inverse as this matrix A, B, C, D. So take my variables here. I can get then that A inverse is A, which is 3, B, 2, C, 1, D, 1. And there's my answer. So if I'm trying to find a 2 by 2 inverse, I'm going to have two equation, 2 variable systems of equations. And you found an inverse. All right. We can double check this on our calculator if you'd like. So if you go ahead and take a look at your calculator. And let me just go ahead and clear this. And if I type my matrix in, so I'm going to go into second matrix. I'm going to go over to edit. And I'm going to keep those in there for later. And so here I have, I'll put it in matrix C. So let me type in my original matrix that I'm trying to find the inverse of, and it's a 2 by 2, so 2 by 2. And then I can type in my matrix, so 1, -2, -1, 3. So there's my matrix. Now I want to find the inverse. So if I quit out of here, I can go to my matrix menu, so matrix, and I'm just going to choose, that was matrix C that I use, so there's my matrix. And then the key that has the matrix on it also is the inverse key. So if I just do C inverse, press enter, I can see that that answer matches the value that I calculated. So that's how you can do an inverse on your calculator. All right, so that was pretty straightforward for a 2 by 2, not too difficult. Now we're going to move on to a 3 by 3 matrix, and we're going to start it off the same way. Okay, so it just has to find the inverse of matrix A here. So the inverse of matrix A means that we're going to set up an equation. So this is matrix A. This is going to be the inverse of A, and that's going to equal, this is the identity matrix, and now the identity matrix is a 3 by 3 matrix. We can see that we have 1s on the main diagonal and 0s everywhere else. Okay. So now that we have this matrix set up, this matrix equation set up, I'm going to solve it using the same method. So I'm going to say row 1 here, times column 1. Okay, let me just highlight that so we can keep track. Row 1 times column 1. That's going to equal this location in row 1, column 1. So in doing so, then I'm going to get A plus D plus G. So my first equation, A plus D plus G. That's row 1 times column 1. I'm going to continue that with every other column with row 1. So row 1 times column 2 is going to equal this 0 in row 1, column 2. So I do that, and I get B plus E plus H. Okay, then I do my last column, row 1 times column 3 is now going to equal row 1, column 3 location. So multiplying that out, and again, if you're struggling with the multiplication, it's this first term times the first one, plus the second times the second, plus the third times the third is equal to that row and column on the other side. And so when you calculate that one, you should end up with C plus F plus I equals 0. And we're going to go ahead and continue that with row 2. So now we do row 2 with column 1 is going to equal this row 2, column 1 location. So multiply that. Then multiply row 2 times column 2 is going to equal the 1 location. And then multiply row 2 times column 3 equals, row 2, column 3, this 0 right here. So we do that multiplication. When you do that, you should end up with 3a plus 5d plus 4g equals 0, 3b plus 5e plus 4h equals 1, and 3c plus f plus 5f plus 4i equals 0. And then finally, let's do the last, row 3 times each of the columns, times column 1 equals this. And that's going to give us this answer. Row 3 times column 2 is going to equal 0. We get that. And row 3 times column 3 is going to equal 1. And we get that. If you need to pause here to catch up, please feel free to do so. Okay. So then what we're going to do with these, we can see again that we have 3 equations in each system of equations, and each system has 3 variables. So I don't really want to solve 3 separate 3 variable systems in my work. That's a lot of work to do, whether you're doing it by hand or even if you're using your calculator and writing them as augmented matrices, you still have to type in each separate system and then find each separate reduced row echelon form. Okay, so I'm going to look for a more efficient way to do this problem. You can still, of course, do it the long way, but we're looking for a more efficient way right now. So let's go ahead and write each of these 3 systems as an augmented matrix. So writing each of these systems as an augmented matrix, what we're going to see is this. Oh, first of all, actually, I have a question. What do you notice about all 3 systems of equations? So just take a moment to look at all 3 systems of equations and see if there's anything that you notice that's similar in all 3 of them. Okay. So one of the things that you may have noticed is you may have noticed that all of the coefficients on the left are the same for every single system. So for the A coefficient here, the first row, we have a 1, a 1, a 1. In the first equation of the blue is 1, 1, 1 for the coefficients. For the green, 1, 1, 1. Then for the second equation, we have a 3, 5, 4 for coefficients, 3, 5, 4. And then a 3, 5, 4. And finally, for the third row of coefficients, we have a 0, negative 1, 0, 0, negative 1, 0, and 0, negative 1, 0. And so we can see that everything on the left is kind of set up in the same manner. And that's what we're going to use to shorten the work that we're going to have to do. Okay? So what I could do here is I could write out each of my systems of equations as an augmented matrix, and then I can solve my augmented matrix for each independent one. So let's see what that looks like. Okay. Zoom in here. So I wrote some of this work down in advance so that we can go a little bit quicker through it. So if I write all the three of them as an augmented matrix, you're going to have these three, okay? So these are the three augmented matrices for each independent system. As you can see, the left-hand side of the augmentation, this is exactly the same as this, which is exactly the same as this. The only thing that's different is the column on the right after the augmentation line. And so what I can do to solve each of these independently is I can work through and I can say, okay, well, what do I want to do in order to get this into reduced or echelon form? So in this first one, what I would do is I would do row 1 times negative 3 plus row 2. Guess what I'm going to do on the blue one? The same thing. Row 1 times negative 3 plus row 2. Guess what I'm going to do on the green one? Same thing. Row 1 times negative 3 plus row 2. Since everything on the left of the augmenting line is the same, all of my elementary row operations are going to be the same. So I go ahead and I do that on each of those. And now we have these augmented matrices. And I can see that I've completed column 1. I have my leading 1 and I have my zeros. So I can move on. The next thing I want to do is get my leading 1 in column 2. So it's just kind of a little practice and refresh of what we've already done. So to do that, well, I'm just going to switch these two. Switch row 2 and row 3. And so I go ahead and I switch row 2 and row 3. And then what I'm going to do is I want to make this into a positive 1 here. So I want to make this here into a positive 1. Oh, same thing on all of them. I'm going to multiply row 2 times negative 1. Row 2 times negative 1. Again, the same thing in every single one of the matrices. So I do that and I continue on. And now I have this. So I've got my leading 1 here. So my leading 1, leading 1, leading 1, leading 1. And I'm going to use that to cancel the 1 above and the 2 below. Hey, guess what? Cancel the 1 above, cancel the 2 below. Cancel the 1 above, cancel the 2 below. So my operations are all the same. Here I'm going to do row 2 times negative 1 plus row 1. Here I'm going to do row 2 times negative 2 plus row 3 for all of them. So I continue. And now I have these three matrices. So I'm almost there. Column 1 is finished, column 2 is finished. I just need to do column 3. I already have my leading 1, so all I have to do is get rid of that 1 that's above. So all I'm going to do here is row 3 times negative 1 plus row 1. And again, same thing for all of them. So continuing on, and I know I'm going through this pretty quickly. You don't have to have this all written down. You can always go back to it, but we're understanding how we can make this more efficient. And so now I've finished it. So now I can see that on the left-hand side, I have reduced row echelon form, reduced row echelon form, reduced row echelon form, actually the identity matrix. And then I have my 3 answers for each system on the right-hand side of my augmentation. So each of these is in reduced row echelon form, and now I can go ahead and I can get my answer. Just remembering my variables, what my variables were. So here they are again. In the red one, the first column is A, then D, then G. In the blue, it's B, then E, then F. And in C, or the green, it's C, then F, then I. Cool. So taking that information now, I can look at my inverse. And so I define my inverse as A, B, C, D, E, F, G, H, I. That was from the very beginning. And then I just plug in my variables that I got from each of my three systems, and I end up with the correct answer for my inverse. Okay. Now I said, we're going to try and find a more efficient way. That was not the efficient way. This is, I'm just going to put it all on the screen here. This is the long way by showing all of the individual steps. And so you're solving 3 independent augmented matrices into reduced row echelon form. But what we noticed is that every single operation for every step was the same on all 3 of the systems. So rather than having to do them separately, we're going to write them together as one augmented matrix, and then we're going to be able to just do the operations on one augmented matrix. So I can combine them like this. I'm going to zoom in now to go back to the first row, the first step. Okay, so what you see here, for every single one, the left-hand side was the same. So the left-hand side of the augmentation. So this was all the same, was the same, and was the same. So the left-hand side of my augmentation remains the same. Then I pull out the first column, and I write that as the first column. I pull out the second column, and I write that as this, I pull out the last column of the second augmented matrix, and that becomes my second column. And I pull out the right side of the augmented matrix, and that becomes my third column. So they're still lined up in the appropriate place, and I know that they come from the first column, comes from the first system, then the second from the second, and the third from the third. And what I'm going to do is I'm going to do these same elementary row operations on this augmented matrix, and it's all going to happen at one time. So before we look more at that, let's look at what we have. So this is matrix A on the left. If you look back at your matrix A from the original problem, and that's augmented. The right-hand side, do you notice that that's the identity matrix? So A is the matrix you're trying to find the inverse for, and then on the right-hand side is the identity. And we're going to transform that into something that ends up having the identity on the left, and on the right-hand side then is going to be the inverse. Okay? I'm going to go real quick back to our last answer. Let's see our last answer. Notice that all of the left sides of these, the left side, that's the identity, and that's the identity. So all of the left sides transformed to the identity, and the right sides were our answer. So the left side is the identity, and the right side is your inverse. Okay? So this is going to be the short way to do it. Now, when you're doing this by hand, yes, you are still going to need to do the elementary row operations. So you're going to say, okay, what should I do first? I'm going to do this. I'm going to do row 1 times -3 plus row 2. So then you're going to end up with, when you do that, you get your first row stays the same. Second row changes. And notice that the second row is going to be the same as the second row of the first step you did separately. So 0, 2, 1, -3. And then we have 1 and we have 0. Our third row didn't change. So 0, -1, 0, 0, 0, 1. And then we do that same second operation that we did. So I wanted to switch those two. So 1, 1, 1, 1, 0, 0, 0, -1, 0, 0, 0, 1, 0, 2, 1, -3, 1, 0. Okay? And then we multiplied this by a -1, so -1 times row 2. And you can see that there are these same operations. First this, then switch, now this. Same operations, and we're getting the same numbers. So 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 2, 1, -3, 1, 0. And double checking, this is the same thing. Notice that now we are looking at, we just completed this one right here. So let's see, does this match what we currently have here? Yes. My first column is the 1, 0, negative 3. So 1, 0, negative 3. Whoops. Didn't mean to do that. My laser pointer here. So 1, 0, negative 3. First column, 1, 0, negative 3. This column, the blue, is 0, 0, 1. I still have 0, 0, 1. Then I have 0, negative 1, 0. 0, negative 1, 0. And I can see I caught my mistake there. This should be a negative 1 because I'm multiplying by negative 1. And then I continue on. So again, now I'm going to get rid of this 2. So row 2 times negative 2 plus row 3. And get rid of this 1. So row 2 times negative 1 plus row 1. And I continue that process all the way until the end. And I'm not going to do it because we've already done it. But I continue that process. In the end, I end up with 1, 0, 0, 4, negative 1, negative 1. 0, 1, 0, 0, 0, negative 1, 0, 0, 1, 3, 1, 2. So on the left is the identity. On the right, this is the inverse. So you would take this and write it just like we did here. And that's how we can find an inverse in a little bit more efficient manner. Fully zoom out on the whole problem here. Okay, everything on the left. This is the left side is the long way. The right side is a little bit shorter way. You can see you have much less to write. Same answer. All right, let's continue. So just in summary, because I see students do this on a test, you do not need to do a 3-equation, 3-variable system 3 times. Do this using what I just said by converting it from A, augmented with identity, to the inverse, or to the identity augmented with the inverse, okay? Do not write all the equations and solve 3-variable, 3-equation systems. It's gonna take you too long. Okay, number 3, find A inverse for this 2x2 matrix. Okay, so let's practice what we just did. So I take my matrix and I set it up. So we said A augmented with the identity. All right, so my A is 3, 6, 1, 2, augmented with a 2x2, so 1, 0, 0, 1. And now I'm going to do my elementary row operations to put the left side into reduced row echelon form. Okay, so let me just put a note of that. Convert left to RREF, which is the identity matrix. Okay, so I'm just going to switch because I already have a 1 in my second row. So I'm going to switch those two. So 1, 2, 0, 1. Now I have my leading 1. Fill in the rest of your matrix. And then I'm going to do row 1 times negative 3 plus row 2. So I end up with row 1 stays the same, 1, 2, 0, 1. And now I have, let's see, times negative 3, so I'm going to get a 0, 0, 1, negative 3. Oh, interesting. So in order to find my inverse, I need to make this side into the identity. And then this side would be my inverse. But notice that I have this 0 right here. I need that 0 to be a 1. But there's no way to make that 0 into a 1, which means I'm never going to be able to make the left side into the identity matrix. Shoot. Did I do something wrong? No, I didn't do anything wrong. Remember, at the beginning of this lesson, I said that there were 2 criteria that had to be met in order to have an inverse. So, to have an inverse, 1, it must be a square. So, is it square? Yes, it's 2 by 2. Second one was the determinant cannot equal to 0. So this is the one that fails in this case. All right? We don't know how to find that yet, but I'm going to tell you right now. Only for the 2 by 2. Anything greater than a 2 by 2 determinant takes more time. So for the 2 by 2 determinant, what you do it shows you down here in the at the bottom, it says that the determinant, where the determinant is AD minus BC. Okay, so this is a formula here to find a 2x2 inverse quicker, but that gives us a 2x2 determinant formula. So if we use this formula, so the determinant is equal to AD minus BC. The A in our problem is 3, D is 2, B is 6, and C is 1. So 3 times 2 is 6, minus 6 gives us 0. So our determinant equals 0, which means an inverse does not exist. Okay, so we can just write for our answer for this problem is that A inverse does not exist. And we'll say why, since the determinant is equal to 0. Cool. So sometimes you're not going to get a determinant. Or sorry, you're not going to get an inverse. All right, so now inside this box, this is kind of a short way to find just a 2x2 matrix, their inverse. Okay, so this formula here, A inverse, is 1 divided by the determinant and then multiplied by the matrix in this format. So you can see what's happening here. So here we start off with A is here and D is there. So A and D here, those two just switch places. Okay, so they just switch places. And then you can see in the given, B, the top right, that one just becomes opposite. So this has become opposite. And the C also becomes opposite. Okay, so you can use this formula if you want to find a 2x2 inverse as opposed to having to do it using the other method. Okay, so that's what happens to that matrix part, and you do 1 divided by the determinant, where the determinant is defined as AD minus BC, which makes sense that the determinant cannot equal 0, because if we had a 0 in the denominator, we would not be able to find the inverse. All right, I know this is a lot of information, but we have one more example to do, and this is solving using an inverse matrix. So we have a bunch of different ways to solve a systems of equations already. So let's quickly just look at those. These are the ways that we already know how to solve systems of equations. So all of these 3 you learned in Algebra 2, graphing, substitution, and elimination. Number 4, 5, and 6 are new. So we've already done 4. We can do Gauss elimination with back substitution, which is just row echelon form. You can either do that in equation or augmented matrix form. Then we have Gauss-Jordan elimination, which means reduced row echelon form. And again, you can do that in equation format or augmented. And then last, we have this matrix equation using an inverse. So this is the newest one. This is what we're going to do in this last example. Okay, so let me go back to that last example. It says solve using an inverse matrix. Okay, so to solve using an inverse matrix, the first thing that we're going to do is we're going to write a matrix equation. Okay, so it's not an augmented matrix, it's different than an augmented matrix. It's an equation for which if you would expand it by multiplication, you'd get the system that you currently have. So thinking about how this works, we do row times column for our matrix multiplication. I'm going to take the first equation here, and I'm going to pull out the coefficients of that for my coefficient matrix. So here I have 1, 1, 1. And normally, or not normally, but what I do with matrix multiplication is I multiply row by column. All right, so this 1 has to be multiplied by whatever I put in the first spot right here. And what I need is I need to get a 1x. So this is going to have to be an x. And then the second term, this 1 is going to have to multiply by the second number there. And I want that one to give me this y. So that's just going to have to be a y. And then this last one gets multiplied by the last number there, which I want that to be a z. So I'm going to have a z there. And that's going to equal row 1, column 1. And this equation equals 2. So 2 is going to be my first entry. So now if I did my multiplication like this, row by column, it equals 2. And that gives me my first equation. So I'm going to an equation. So my second equation is going to be 2, negative 1, 2. And if I multiply this row by column, so that's going to be 2x minus y plus 2z, that equals 1. That's going to have to go my second entry. And then I do my last equation, becomes -1, 3, -2 times xyz equals -2. So this here is your coefficient matrix, which we did also have in augmented. This is your variable matrix. And then this is the constant matrix. Okay? All right. Now, with matrices, there is no division. Okay? So we have no division in matrices. Okay? Which means we have to do everything by multiplication. So I'm going to think about, how do I get rid of something with multiplication? To get rid of something, what I do is I multiply by its inverse. So what I want to get rid of is I want to get rid of this matrix on the left so that I can have just the variables remaining. Okay? So to get rid of a matrix, I multiply it by its inverse. Okay, so let me go ahead and just define some variables here, or some matrices here. So I'm going to let the coefficient matrix be matrix A. I'm going to call the variable matrix matrix X, capital X, not the variable little x, and I'm going to call the constant matrix matrix C. And I'm doing that just so I don't have to write so much. Okay, so what I need to have is I need to be able to get rid of matrix A so I can solve for matrix X. So I'm going to multiply this by the inverse of A. Now I multiplied it on the left, so I have to multiply on the left as well of matrix C. And the reason for that is because of matrix multiplication. With matrix multiplication here, we know that since A inverse is 3 by 3, and then the C matrix is 3 by 1, because the two 3's match, I know I can multiply it. If I were to put it the other way, let's do that for a second. If I did C times A inverse, C is a 3 by 1, A is a 3 by 3, these don't match, and so that would not work. Okay? But I know, so this is going to work, so A inverse is going to cancel matrix A, and so my equation that I'm left with then is that my variable matrix X is going to equal A inverse, I'm going to put that in blue, A inverse times matrix C. And so that's what I have to do now, is I have to find A inverse and I have to find matrix C. Okay, so let's go ahead and set up finding A inverse, and then you can do it by hand if you want to practice it, but we're gonna do it on our calculator. So to find A inverse, we're going to set up matrix A, so A augmented with I, and then we're going to convert it to the identity, and then the inverse is on the right. So matrix A is 1, 1, 1, 2, -1, 2, -1, 3, -2. Augment it with the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? I'm going to use my calculator now. So the way that I can use my calculator is if I want the left-hand side to turn into the identity matrix, then basically I want reduced row echelon form. Okay, so I'm going to go ahead and do RREF and type this into my calculator. So let me just slide that over for a second. Slide it over and bring it up there. Open up my calculator, and on my calculator, I put this into, so I'm going to go to my matrix. I think I put it into matrix A. Oops, let me press enter right now. Yep. Okay, so this is what I have in matrix A. So it's a 3 by 6. Okay, that's the same matrix that I have there on my screen, and I want that to be in reduced row echelon form. So second matrix, math, and I want reduced row echelon form. So enter on reduced row, and I want matrix A, second matrix, and I want A, close my parenthesis just for good measure, and enter. Oh man, it gives me all these decimals. Well, my calculator can change my decimals to fractions, so just press the math key, And then you can see that it's changing it to a fraction. So press enter and it's changing that answer to a fraction. That looks much better. Okay, so now this is my answer, but I have to pull out what part of this is my inverse. So go ahead and write that down on your paper. So what we have now from our calculator, that gave us this 1, 0, 0. Then I had negative 4/3, 5/3, 1, 0, 1, 0, 2/3, negative 1/3, 0, then 0, 0, 1, 5/3, negative 4/3, negative 1. There's my augmenting line, even though my calculator doesn't show it. So that means that this now is my inverse because we converted it to identity on the left, right? So identity is on the left. Here's my identity. And the inverse is on the right. So therefore, A inverse is negative 4/3, 5/3, 1, 2/3, negative 1/3, 0, then 5/3, negative 4/3, negative 1. Make those a little bigger. Okay? Okay, that was just my inverse. Back to the problem. So now I need to take this inverse and I need to multiply it by c. So x is going to equal this inverse. So negative 4/3, 5/3, 1, 2/3, negative 1/3, 0, 5/3, negative 4/3, negative 1, multiplied by matrix C, which I have above is 2, 1, negative 2. Cool. And all I have to do is multiply this now. So again, we can multiply by hand, all right? But we're gonna use our calculator to multiply, but you are welcome to do it by hand just to check to make sure that you can multiply with matrices in practice. But if I open up my calculator, so I have the inverse. I'm gonna do the inverse. And I can do that by just telling my calculator to do that. And then I'm going to find matrix C. So I'm going to type in matrix C. So whoops, matrix. And I'm going to edit and add in matrix C. So my matrix C is a, oops, I don't want to change A. Second matrix. Let's edit. And let's do D. And so D is going to be 3 by 1. So I have 2, 1, negative 2. Okay, all right, so now I'm going to go to second matrix. I want the inverse of A, which I did not store in here, did I? Nope. Okay, so let me put A in here. I got to do one more in here, put that as E on my calculator. So A is 3 by 3. And A is 1, 1, 1, 2, negative 1, 2, and negative 1, 3, negative 2. Okay, so there we go. So now I can go to math, and I want to go out of there. I'm going to first choose matrix E, and I want the inverse of that one, so the inverse, and then times matrix C. So second matrix, which was my D that I put in here. And if I press enter, that's going to give me my answer. So matrix X is equal to negative 3, 1, 4. Which means then for my system, my answer is negative 3, 1, 4. Now the calculator did a lot of that for us, so I am going to actually show that we have A inverse times C and we get the right answer. So over here on the right, so now X, let's just check it by hand. X is equal to, so now this row by column, so we have it right here, let's do it by hand, row times column. So I have negative 4/3 times 2 plus 5/3 times 1 plus 1 times negative 2, right? That's this row times this column. That's going to be my row 1, column 1. Then I do row 2. So this row 2 times column 2. is 2/3 times 2 plus negative 1/3 times 1 plus 0 times negative 2. And then row 3, column 1, so 5/3 times 2. Oops, I'll just do minus. No, I'll do plus. Plus negative 4/3 times 1 minus 1 times negative 2. And so if I calculate each of these, then let's see, that's negative 8/3 plus 5/3 is negative 3/3. Negative 3/3 plus negative 2 would be negative 3. So that's negative 3. If I calculate the second row, it's a 1. And if I calculate the third row, it is a 4. So that also verifies that it is correct. All right, so sorry that it's such a long video. There's a lot going on here. If you need to go back and watch more, watch it again, please feel free to do so.